Hello, everyone. Welcome back. Today, we have a very exciting conversation. We are joined by my friend Joe Tegtmeyer. Joe is a retired Air Force pilot, Tesla Giga Texas drone historian,
Mhm.
SpaceX fan, and expert. And we are going to cover a few very interesting topics. Today, we're going to talk about the recent Starship program milestones, the technical challenges that SpaceX is facing, what their timeline looks like for 2026, and my favorite part of today's chat, what the Starship orbital flight return looks like based on Flight 11's telemetry data. So, without further ado, Joe, welcome back. Thank you for joining me.
Hey, everybody, and thanks for having me on. It's a great day to talk about Starship.
Absolutely is. And it's a beautiful day down here in South Florida. How's the weather over there where you are?
It's actually not too bad. I flew Giga Texas today. It was a little foggy, so after that it cleared up, but it was a little challenging to fly today.
Can't wait to see that flight. So, Joe, let's kick this off. Let's talk a little bit about the milestones of SpaceX.
Okay, well, specifically the Starship program is what we're looking at, and just a couple of things is hopefully if people are watching, if they have any questions, please put it in the chat, and I will try to answer that either while I'm going or at appropriate time. The second thing, what we're trying to talk about here is the Starship program in total and the phases that they've gone through right now. They went through the suborbital test hops, then they went in through the version 1 prototypes, then they moved to the version 2 prototypes, which they just wrapped up with Flight 11, and now they're getting ready for the version 3 prototypes. And along the way, they've done a lot of changes to the booster, to the ship, to the entire system. And I know a lot of people have talked a lot about what those are, but I'm not too sure if people understand why they did it. So I want to try to dive a little bit more, not super detailed. My goal is not to turn everybody into aeronautical engineers or astronautical engineers. You know, people spend years going to school and getting master's degrees, PhDs, and all that stuff. So we're not going to do that, but I am going to use a little bit of examples just to give a few kind of fundamental principles so that when we talk about what they did with the booster and the Starship, it kind of makes sense of why and how that leads to what we're going to be doing. So hopefully that makes sense.
Absolutely. I mean, I'm a space kid from the 70s, 80s. I'm always like being fascinated by space science, anything related to space, and having the ability to have a conversation like this one where we can dumb it down a little bit for folks like me, but at the same time, keep it technical enough so that I can have some fun. I think our audience is going to appreciate that.
Yeah, well, I hope so. So anyway, if people have specific questions, I'll try to answer that. But a couple of the basic fundamental principles that I would like to talk about that has to do with the development of the Starship. First of all, is just the basic concept of what is a center of pressure, a center of gravity, or more appropriately, the center of mass, and how does that work with the Starship program and also with airplanes or anything else that flies. And then I also want to talk a little bit about why rockets are very different from airplanes, and then I'll kind of bring it all together. But fundamentally, you have two kind of centers of something on any device or any object that flies. You have one, which is the center of mass, and it's kind of like if you take the entire shape of the item, whether it's an airplane, a rocket, whatever, you can find a central point where all of the mass seems to be concentrated. And that's very important to know where that is on the airframe itself, because that's going to drive a lot about the controllability that you use or you have on that aircraft or that airframe. The other basic concept is the center of pressure, and that's where if you take all of the aerodynamic forces that are acting on that body, you can concentrate those down into one single point, if you will. And the relationship between the center of pressure and the center of gravity on this airframe or on the rocket is critical for whether or not it's going to be stable or unstable, and whether or not you have full control, partial control, or if it just is uncontrollable. And generally speaking, you want to have the center of gravity slightly ahead of the center of pressure in the direction that you're flying or you're moving. in an atmosphere. And that's very important to understand. And kind of an example of that is, here's an airplane I used to fly. And with airplanes, they're designed pretty much to fly in one direction. You don't normally see them going backwards, which you're going to see with the booster and some of the rockets that SpaceX uses. So the direction of motion, you want to have the center of gravity slightly ahead of, or a certain distance ahead of, that center of pressure. And that allows for the proper controllability. And with an airplane, I know this looks like a fighter, it's a T-38, and it can do a lot of maneuvering, and it's very high powered. But generally speaking, if you think of like a commercial airline or so, they generally work within a very small area of the atmosphere. And it's from the ground level up to maybe 5 to 7 miles maximum in height, which would be somewhere around, I don't know, let's say, 10 kilometers, 12 kilometers, something like that. And they also tend to operate within a horizontal slice of the atmosphere, which means that they're generally flying in this direction, parallel to the ground. So that way it has, the atmosphere is pretty much consistent. It acts linearly, more or less, with the kinds of forces or the density and that kind of things. And the way the aerodynamics work with airplanes is pretty well understood. We've all flown in it. We kind of understand how that works. When it gets to a rocket, it's very different, because the rocket, and I'm going to use a Falcon 9 here as kind of an example, and you can see that on the screen here. And you can go to the next slide real quick. It has a variety of different modes of flight. One, it's unpowered flight, and it's going up. And while it's doing that, it's also using a lot of the fuel very, very quickly. So when you first start off, say your center of gravity is here, but you're using the fuel at a very high rate, much higher than you would with an airplane. And that center of gravity is going to be changing a lot. And in this case here, when you have the upper stage, the center of gravity is actually going to be moving upwards, which can be a problem. But the other thing to keep in mind is that center of pressure initially is based on a couple of things, one of which is the density atmosphere that you're in. But as you are climbing in the altitude and going through that vertical volume of the atmosphere, that density starts to rapidly go away. And if you think about it this way, is at 5 kilometers, which is about 18,000 feet, give or take, you've lost half of your atmospheric density already. So if you've ever gone onto a mountain, you can feel it. It's harder to breathe, and it gets colder and all that. And that's just because of how rapidly that density changes. If you go up to 10 kilometers, you've lost more than 75% of the atmosphere. And at 10 kilometers happens to be, with the Starship, about when it is going through maximum dynamic pressure. And you'll hear that in the callouts when you hear or watch the launch. And that happens to be where, as the velocity is going faster, you would think that the forces are getting stronger, but the density is starting to drop off. So at that max Q is that point where those forces reach a maximum, and then they start dropping off rapidly because that density goes away. So anyway, the rocket has to deal with massive changes in center of gravity, massive reduction of and then elimination of the center of pressure. And you also have the engines that are providing that controllability. So it's very different than what you would experience with an airplane going horizontal through the atmosphere and keeping the density relatively constant as it's flying. Now, you have another aspect of rockets which are different, and that is, if I can get this off, they change shape. Airplanes generally take off and land in the same shape that they started with. But with rockets, when this happens, now you've changed the whole dynamic of these two completely different systems, and you have to take that into account. Now, with SpaceX, they bring the boosters back. So initially, everything is designed to fly this way. When it separates, the booster at a higher altitude will do its boost back berm. It'll come back and it will start coming through the atmosphere. And it doesn't really have much aerodynamic control at that point. So it uses the thrusters to properly orient it. And then it generally gets to some sort of an orientation like this here. and it will just basically fall through the atmosphere. And then as that density comes back up, it starts gaining more and more of the control because of that center of pressure building back up. The other thing that you have to keep in mind is, of course, that center of gravity has changed dramatically now. So before, as it was moving up, because you had the upper stage that was full of fuel and everything, as soon as the separation happens, that center of gravity drops back towards the heaviest part of the booster, which is down this part. But that's okay, because if you remember, I said controllability has to do with the relationship between center of gravity and center pressure. Well, now it's going this direction, downwards. So the center of gravity being ahead of the center of pressure is actually what you want for stability. So they take that into account, and that's pretty much how the booster comes back down.
So I have a dummy question, right?
Okay.
Let me pull my rocket here, the
Okay.
Falcon 9, right?
All right.
And when the rocket's taking us, right, it goes like that. And how can they control it doesn't go, in a different direction? We have wind, we have the rocket propellant changing, it's burning off, the vehicle's becoming lighter and lighter as it climbs up. Then it hits different levels of the atmosphere, which also adds to complexity. How? Because I know that when it's coming back, they're using the boosters to control, and they have these little things that go psh, 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 and move it sideways so that it can rotate, right? And I'm going to use all these technical terms that I have in my
Okay.
pocket right now. Okay.
All right. I'll try to use that.
But how is it? Because the rocket is so um, well balanced, right? We have race cars. We control race cars. I used to race road racing, and race cars are very balanced in a certain way, and you can predict where they're going based on that balance. How do they manage that with the rockets?
Well, that's a good question. A couple of things. First of all, in a race car, it does use fuel, but it uses at a relatively modest rate compared to a rocket. And the changes in the weight of the race car, it happens and it does affect handling and everything, but it's at a much slower rate than a rocket, which is doing, tens of tons a second of the propellant. On the way up, predominantly what it uses is the engines. And the Starship, for example, there's 33 engines. They have an outer ring of 20 that are fixed and they cannot move. But the inner 13 can actually move. They're called gimbaling. And by changing direction of where that thrust is coming, they affect the rocket. So for example, if the engines are thrusting this direction, then the rocket's going to want to go like this. So it's kind of like moving the bottom of it in the direction of the thrust. So the top is rotating and back and forth. So they use that gimbaling as they are ascending through the atmosphere to control it. Similarly, when it's coming back down and you see that landing burn, they also use the gimbaling, because pretty much it's slowing down to the point now where you're not going to get much aerodynamic control. You're just going to have to use the rocket engines themselves and turn them in a certain direction. You're kind of like balancing a pencil with the rockets. So as it moves this way, you want to push the tail down, and if it moves this way, you want to push it that way. So that's what's happening with the rocket's engines moving. Now you asked about the thrusters.
The ion thrusters, or
yeah, yeah. So sometimes those are either called reaction control systems, and they use maybe kind of a gas like a nitrogen or so, which would be like a low temperature
on this
system.
one. On this one, they're on the ship, on the top part of the Falcon 9 where the Dragon is, right? Because there's some thrusters in the body of the booster as well, besides the fins, right?
Yeah, they actually have thrusters on both the upper stage thrusters, and they have them on the Falcon 9 first stage. And on the Starship, they also have them on both, but they use a slightly different system. So instead of having like gas that's in a container called a COPV, which is used to push out at different parts of the rocket, while it's way above the atmosphere and the density of the atmosphere is so low, you can't move it with aerodynamics, and the engines are not on because they're pretty much free falling back. So they use these cold gas thrusters to push parts of the rocket around to reorient it in the direction that it needs. The Starship is very similar, but instead of having containers full of this cold gas that you use for the thrusters, instead they use something called ullage, which is basically the gas inside the tanks themselves. And they basically open valves in a certain place. lets some of that gas out, and that pushes the booster one way or the other, or the ship one way or the other. And I don't want to get too deep of why they made those choices, but
Mhm.
effectively, it's the way that you control the rocket or the booster when it's too high and it doesn't have enough of the density of the atmosphere to have much aerodynamic control. So you'll see that with the booster when it does its boost back. It uses the departure, the hot staging of the the Starship to help push the booster in a certain direction, and they can control it to some degree. And then they get the engines on, and then when the engines are going, they can use the gimbaling to fine tune its flight path. But once the gimbaling, or once the boost back is over, you'll see that the engine shut off, and then now they have to use something to reorient the booster. And you see a lot of these kind of shoots of gas coming out from the booster, and that's that ullage gas being pushed out, and it's reorienting the booster to get into the proper orientation for it to return back and get ready for its catch.
That's when we see on the atmosphere the what they call the jellyfish, right?
Well, not exactly. The
Not
jellyfish is
exactly.
actually something different. The jellyfish is caused by the exhaust plume being illuminated by the sun, and the way you see that most of the time is that the sun has gone below the horizon for
Mm,
you at the ground. But when the rocket gets high enough, the plume is illuminated by the sun, and then that
right.
gives you that jellyfish. For the return with the ullage thrusters on the booster, what you'll see is like these long streams of gas coming out from it, and
Oh
sometimes it
yeah,
almost
yeah.
looks like it explodes, but it's really that gas which is pushing the booster around to get it oriented.
Excellent. Um,
Okay.
uh, should we stay on this slide or go to the next one?
Let's see. You can go to the next one and see what's on there. Yeah, so a couple of things that I want to talk about real quick on the booster of some of the work that they did in the 11 flights that they've done up to this point to kind of refine that booster design. One of the biggest ones is, if you recall, after flight one, they did not have a hot staging ring. It was just like a top of the Falcon 9. And the idea was that they were going to basically use kind of a centripetal acceleration and cause a rotation and have it separate, and that rotation would make it separate. And that was quickly abandoned. And I don't think they ever, I mean, Flight One never actually got to the point to really try that. I know some people have talked about that, but it never
Mm.
got to the parameters to release the ship. So they never really tried that, but they decided that was not a great idea. So instead, they wanted to do something so that they could keep the booster still boosting and also light the engine and separate them by using the exhaust of the upper ship, the Starship, to separate them. The
Is
problem is that you need to have some place for the exhaust to go. And the top of the booster's got a lot of sensitive equipment, motors for the grid fins, all that stuff, and they need to protect it. So they came up with the hot staging ring concept. And that was sort of an after the effect ad, and it was after they designed the booster. So if you go back to the discussion again, why I was talking about the center of pressure and center of gravity, is that the booster before it had the hot stage was designed in such a way that it was coming back in. The center of gravity and the center of pressure were separated correctly, and it allowed them to have that stability. When they added the hot staging ring, it moved the center of gravity farther towards the top of the booster, which brought the center of pressure, center of gravity so close together, or maybe switched positions, so the booster would be completely uncontrollable. And we actually saw that to some degree with flight, I forget which flight, but it was Booster 10. And when Booster, it was the first one that came back, and I think it was the first one, or maybe the second one that came back to try to land in the Gulf as part of the plan.
okay.
But towards the end, it started getting really squirrely, and it ended up losing control. And there's a lot of speculation that the hot staging ring never came off. So the aerodynamics of the booster were really upset, and it was unable to control itself. So that's why now what you see is, after the hot staging happens, the booster turns around. They use the engines with gimbaling for control, and it's way above the density that you need for any aerodynamic control. So they bring it back, and as soon as the boost back burn is over, the first thing they do is separate the hot staging ring. They want to get rid of that so that the booster can orientate itself and then have that center of gravity and center of pressure in the correct orientation to allow for the controllability to come back. So they had to jettison the hot staging ring because it was a temporary add to an existing design that wasn't really built to have that much mass at the top. Does that make
Mm.
sense?
Yeah. So does that mean that they're going to get away from the hot staging ring altogether?
In a way. So the new design, which is based on all of the lessons that they learned with the booster and the hot staging ring up to this point, it incorporates basically a hot staging ring into the design of the booster. So the booster is designed from the beginning with this hot staging ability so that the ship can be connected to it, and the ship can still do the hot staging to separate from the booster, and then the exhaust has a way to go out, but it doesn't require any change. It's already built in for the center of gravity, center of pressure for that controllability.
Okay.
And a couple of ways that they had to accommodate that is the very top of the methane tank is basically what the exhaust of the Starship thrusts against. So that's kind of an interesting design. They've recently put some pictures out where they showed the reinforcing of the top of the methane tank to withstand the exhaust of the Starship for it to come across or to come apart. And what would be the hot staging ring, which is now part of the booster, looks like a truss with a lot of triangles in it and a ring on the top. So it has plenty of room for the exhaust to come out, and it looks a lot like the old Soviet rockets that did the same thing with hot staging. They had this truss structure. But the lessons that they learned by using the hot staging ring and all the data that they got informed the design of the new booster. And so that's pretty cool. One other thing, are there any questions on that? Or
Not on the chat right now. I think we can keep going.
Okay. Another design of the booster, and you can actually see it on this picture here, is along the sides of the booster, they added something called chines, and they are kind of like small stubby fins on four sides of the booster. And they kind of run up about a third of the length of the booster on Starship, or on the Super Heavy. And that does a couple of things. One is it allows them to put the composite overwrap pressure vessels, which have necessary gases for doing the relights of the engine and doing some of the fire suppression system and all that. Anyway, they kind of attach them along the side of the booster, and then they cover them with these covers that are called chines. But they also do something else, is they affect the aerodynamics of the booster in a couple of ways. One of ways is that it helps to kind of re-energize the flow around the bottom part of the booster, and it gives it more of its aerodynamic controllability as it's coming back down. It also allows it to make a little bit of lift, so it allows the booster to actually fly sideways. So they're like stubby wings, if you will. So they added those onto the booster. They've worked a little bit on the design of where they need to be oriented and how big they are. But it was one of the things that they tested throughout the entire system, or the program up to this point, to make sure that they were all set the way that they needed to be. And it informed what's going to happen with the new design of the booster, because you're going to notice that the new design booster are slightly different. They're not symmetrical, they're actually asymmetrical, and they're designed to help with that aerodynamic the flow, and also with the lift of the booster to help when it's coming back down.
Man, it's fascinating. I would give anything to be like a fly on the wall on that meeting where they decided to make those changes, right? Like, how can you
Yeah.
come up with those changes? It's incredible.
Yeah, well, that's one of the strengths, I think, of the way SpaceX approaches the iterative, agile kind of process of design. Is, the traditional way of building rockets is they use kind of like a waterfall, which is a very structured project program management kind of approach. And you
Hmm.
have to go through the entire process, and you come up with your design. And, it takes a lot more time, it's more
Hmm.
costly. And then you may end up with a design that doesn't completely work. So you have to kind of rework it. Whereas with the iterative processes, they can try all kinds of things, add a hot staging ring, change the chines, add them on, whatever, and then go flight test it and find out what really works and what doesn't. And
Hmm.
I think recently, I'm going to get his name wrong, but I think it's Gerstheimer, who works for SpaceX now, used to be with NASA, talked about how they learned in the actual booster flights that they had more controllability of the booster than they had in their simulations. And they wouldn't have found that out if they hadn't have actually been flying real hardware. So, I think there's a lot of benefit for that.
Yeah, definitely. Especially the way that SpaceX is doing. It's just like one week after the other, they're
Yeah,
flying something. I mean, it's just
yeah,
insane. The rate of how they're testing is just insanity.
yeah. Now there's one other thing that they did with the booster that I want to highlight, and that's what this picture here is trying to discuss. If
Mhm.
you remember a couple of flights ago, I think it was flight 9 with booster 14. It was the second time they flew booster 14. It was planned to come back and land in the Gulf, but they said that they were going to be experimenting with the angle of attack of it coming back down. So why would they do that? And the reason why is that there's a couple of reasons why. One of the reasons why is, if you recall, several flights before that, when the boosters were coming back to be caught, actually starting with booster 12, after they caught the booster, they realized that the engines were warped and they had misshapen, they kind of plastically deformed.
Mhm.
And part of the reason why is that as the booster's coming back, if it's got a low angle of attack, which means that with the direction of flight and the longitudinal axis of the booster are pretty much aligned, then this is what sees most of the shock waves and most of the airflow. So this part gets extremely hot, and you actually saw that with boosters coming back. Remember how they glowed
Mhm.
and it looked like the engines were on, but they weren't. And the reason why is that you get this compression heating really concentrated on the engine compartment because of the low angle of attack. So
Yeah.
that actually warped the engines. And if you recall, after the booster 12 was caught, people noticed that it had warped. And Elon actually talked about that. He said, yeah, there's some things that we can do to try to address that. That's fairly easy. Well,
Mhm.
one of the ways you do that is you change the angle of attack. Another reason why you want to do that is, you imagine that as this is going through the atmosphere is interacting with this, and there's a lot of drag. There's body drag, which is basically the shape of the object. There's drag because of lift, because of those chines and other parts of the booster. It actually is producing lift. Whenever you produce lift, you also produce something called induced drag. So you have all these various forces that are trying to slow it down. But one of the most important things is the amount of surface area that you expose to that relative wind or the velocity vector. So instead of coming down like this, if you flatten it out, you have a lot more of the atmosphere interacting on the booster, which helps to slow it down. And
Mhm.
a benefit of that also is you need less fuel in the booster to do your landing burn. So it helps with the fuel, it helps with letting the atmosphere do more of the work, and it helps by reducing the heat loading on the end of the rocket. But there is a problem, and booster 14 encountered that problem, and that is this increases a lot more stress on the actual object, in this case, the booster. And
Mhm.
there was so much stress based on the higher angle of attack that they used on booster 14 that the methane tube inside the oxygen tank actually broke. So you
Mhm.
can imagine that they're bending the booster, and it bent so much that it broke that fuel line inside. So when they went to light the engines, you had a bad fuel oxygen oxidizer mixture, and it blew up. So
Mhm.
their solution on that was to reduce the angle of attack to not as aggressive. And we
Mhm.
saw that booster 16 and then booster 15.2 did fine. But this experiment kind of informed the new design of the booster. And one of the biggest design changes directly for that is that the fuel tank or the fuel line inside has been beefed up tremendously. So it will allow it to have higher angle of attack, which will give all the benefits that we talked about, but
Okay.
without overstressing it. And to put it into perspective, the new fuel line inside the the methane fuel line inside the oxygen tank of the Super Heavy booster is the size of this Falcon 9 booster. It's like having a Falcon 9 inside the booster.
Wow. Joe, I'm curious about one thing. How do you know so much about the small details, the very obscure details of the construction of the ship? Is it public information that anyone can find, or is it because of the people you know at SpaceX that you know so much about the internal components right now?
Well, some of it has to do with there's a pretty good, robust online system of channels that everything from NASA spaceflight, you have Everyday Astronaut, Marcus House, What About It channel, you have the Tomorrow channel, you have the Space Engineer, who is one of the guys that we're going to be using his work here. There's a number of different channels that provide a lot of this information. The Ring Watchers are great. Chrome Kiwi is great. Ryan Hansen Space is great. CSI Starbase is also very good. So if you watch a lot of these, you can get a lot of these details. The other thing is that this is sort of my background anyway. So
Mhm.
it's rockets and astronautical engineering is where I started. So it's
Yeah.
kind of in my wheelhouse.
No, the reason why I ask is because not everyone is a highly technical person, and I think this is fascinating because I know a lot of this information because I speak a lot to you, but I also watch probably half of the channels that you just mentioned also frequently, right?
Yeah.
And I want to help. Like the reason why I wanted to do this together with you is because we're almost opposites in the sense of the technical expertise,
Mhm.
right? My background is not in aeronautical engineer, and I want to bring space to people that are common like me, that but are very interested in it because once we start going to space, they're gonna need every kind of person, not just the
Absolutely.
super PhDs, right? They're gonna need
Right.
the other people because you don't want the, let's call it, the big brains working on things that are not necessarily the best use of their skills, right?
Mhm.
But everyone's going to need to have some common knowledge about these things so that they can also collaborate with, whether it's an emergency, whether it's providing feedback from a different perspective, right? Because
Mhm.
I've heard stories about people in Starbase that are working for SpaceX that are nowhere near um, responsible for a particular engineering challenge, but they have proposed solutions that have been adopted by the engineers, right?
Mhm.
So I think that's fascinating. That's why I was asking you because I want to encourage people that don't know as much to still dig in and find this information because at the end of the day, it's probably going to prove very, very useful, right?
Mhm. Yeah, well, that's actually a great point. And here's a kind of an example on that is not everybody has to be a rocket scientist or a rocket engineer to work for SpaceX. And one of the best examples of that is all the people that are doing a lot of the welding. There's a lot of oil and gas industry around this part of Texas, and many of the people came from that. So their expertise in being able to do those kinds of welds, to use those kinds of materials, comes in extremely handy, and they can still build our rockets that are going to go to Mars and help us colonize Mars and make space a place that we all live and work in, is very true. So, and your other point is it's going to be important if we're going to colonize the moon, Mars, or anything else to have a wide variety of people that have different skill sets. And to your point is it's not sustainable for us to have a handful of highly technical, highly trained people that go through years and years of training. We can't sustain that. So at some point, it's going to have to accept a lot of different people. So I think
Mhm.
that's one of the things that SpaceX is trying to build.
Excellent. Thank you so much. I was always curious about that thing. Uh, I don't know if you want to jump into the other milestone
Yeah,
slide here.
yeah, this is okay. I want to talk a little bit. I know this is not a Starship. I get that, but it's the best thing I have right now for an
We're
example.
gonna get a Starship for the next one.
Exactly. But what I'm trying to show you here is now instead of talking about the booster and hopefully this gives you a little bit of insight to the work that they've been doing over 11 flights to develop the booster. For the ship, there's been a lot of things that they have done, but perhaps the most visible change on the ship that everybody notices are the forward flaps. And there's a couple of reasons why they changed those. And if you go to the next slide real quick, I don't want to go into this equation. If anybody wants to go into that equation, I can. But there was a fundamental flaw in the design of the original starships, the ones that would be considered the version ones that flew for the first, I don't know, 6 flights or so. And that fundamental flaw was the forward flaps, as you can kind of see here. Now, what I'm trying to show here is, and what most people think about is, first of all, is they remember the flaps burning and melting off. And there was a lot of discussion about, are the heat tiles good enough? Are they going to be able to survive? All that stuff. Well, that is one of the big flaws that they had. And to address that flaw is that they moved them farther away from the plasma flow, so more to the leeward side. So instead of 180 degrees, they're now about 140 degrees. They reduced the size of the flaps themselves, and then they moved them higher up on the nose. So what did that do is it reduced the body to flap interface, which was sticking out into the plasma, getting a lot of that heat flux. And we've seen with the last couple of flights that have re-entered okay, that seems to work out really, really well. But there was another flaw that is less known, and what they really needed to do to address the controllability of the Starship, especially as it was coming back through the atmosphere, going through the plasma field, as the density of the atmosphere was starting to increase, is that the forward flaps became more and more, capable with the aerodynamic forces, because you have a high velocity and you have a growing, although slow, but you have a growing amount of that density of the atmosphere. So what was ended up happening is that original design, in addition to creating a lot of that heat flux, and we saw the melting, but it also kept trying to pitch the Starship up because there was too much forces on the nose relative to the heavy rear of the Starship. So it kept wanting to do this. And that is not ideal because it exposes more of the bottom of the Starship to the plasma. It also makes the rear fins have to work a lot more, which means that they have to counter it, which means that they have to be out farther, which means that they have even higher heat flux themselves. So
Right.
to address this pitching moment, which was really the controllability issue for the original Starship, by moving the flaps where they did, higher up, smaller, more into the leeward side and more out of the airstream, they corrected that pitching moment, and now the Starship itself is more controllable. And we saw that through the last couple of flights where they were doing a lot of really high angle big maneuvers at hypersonic speeds. They were actually moving the Starship like this through the atmosphere. They were pitching it up. They were doing a lot of stuff, really stressing the system, but it really proved that they gained that controllability by changing those forward flaps. So that is one of many, but probably the primary reason why the flap designs changed on the Starship. Does that make sense?
Yeah, it does bring me a question to mind. Will that design, if they decide to stick with it, those changes, would it be different when they go to Mars because there's less atmospheric constraints?
It'll still affect it the same way, but it's just the rate of change and the maximum value of what that density is going to be. At the surface of Mars, roughly, it's about 1% of the density of the Earth's atmosphere. So it would be the equivalent of you going to about 100,000 feet. So if you went to 100,000 feet, you would experience the pressure of Mars, which would not be very comfortable.
You're not calling me fat, right?
No, no, no. But
No, I
yeah, if you
get you.
remember Total Recall when they fell out into the surface and their eyes were coming out, whatever, it would
Yeah,
not be fun.
yeah, exactly. No, 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 absolutely.
Yeah,
Okay,
but
right
even
on.
with that density, if you have a high enough velocity, because if you go back one slide, I'm going to go geeky real quick, but if you go back one slide, you'll see the equation, and this is the equation for drag, but the biggest thing to notice is that you have the rho, which is the density, and then you have the v squared. So as the velocity increases, then the effect on the overall drag, the heating, and the aerodynamic forces on the ship go up tremendously. And the density, it does have an effect, but it's not squared. So the only thing that makes the density more important is the fact that it rapidly goes to zero. So if you have a zero in your equation, it makes it zero. So there would be no drag because there's no aerodynamics. But the
Right.
velocity is really, really important. And it's that velocity that causes the plasma that we see. And you
Right.
would still get that on Mars as well. In fact, it would be probably worse because Mars' atmosphere is mostly carbon dioxide. And when you have those high velocities, you ionize the gas, you break it apart, and the electrons from the molecules come away. So you have this plasma. And what that does is it creates a very strong atomic oxygen environment, which rapidly rusts and rapidly combusts things. So it going through Mars, even with the density of the atmosphere so much lower than Earth, is actually harder and
Hmm.
more difficult than going through the Earth.
Okay.
So most of what they are doing, and we're going to talk a little bit about heat shields, but a lot of what they're doing is with Mars in mind. And a lot of the tests they're doing is in a CO2 atmosphere, not just a nitrogen oxygen one that we have here.
Got it. Right on.
All right. Are there
Um,
any questions or am I just going crazy?
no, no, we're good. There's some fun comments on the chat, but not specific questions for you yet. I'm pretty sure
Okay.
a lot of people are probably waiting to see that animation that we're going to
Okay. Well,
cover a
sounds
little bit
good.
later.
Well, we can move forward. We've spent a lot of time on this one.
Okay.
Okay,
So,
so we talked about the booster design. This is the redesigned one. You can see there's a lot of differences. We talked about the grid fins on the top a little bit. They've reduced them to 3 for a variety of reasons. You can see that sort of built-in hot stage on the top, and you can see the chines that are a little bit different design along the sides. And of course, the engine compartment is significantly different. But all of the tests that they've done up to now through Flight 11 has helped inform this design.
gotcha. Okay, so I think this is a good time to change to the next topic, which is
Sounds
going to
good.
be the technical challenges, right? So I have a question for you about this. Like, what are the top engineering hurdles for the Starship program right now?
Okay. Well, there are a lot of them. So, just saying there's one or two is really kind of glossing it over.
Hmm.
I would say the first one to keep in mind, and we're going to talk about that a little bit when we get to what to expect in 2026. But just keep in mind that in engineering, when you change designs, you usually want to change a few parts at a time so that you can isolate. Did you create a problem? Did it interact with other systems in a way you didn't expect? Whatever. Well, SpaceX does it completely different. They just jump all the way in. So we have a completely new booster. We have
Okay.
a very new ship that has got the data from before, but they're also very new. And we also have a new tower. We have a new orbital launch site, everything. So, one of the biggest challenges is how do they build on what they've got with completely new hardware? So just expect that there's going to be some challenges that maybe come up that you might go, well, they've already done that with the previous versions of the ship or the booster. Why did they have that problem? And it's because they've changed so much.
Hmm.
But probably the two biggest technical challenges that are ahead of the Starship program, one is the heat shield, and that's what we're going to talk about here a little bit. And the other one is orbital refilling, and we'll get to that in a moment. But what this is showing is this is Ship 38 from Flight 11 as it's getting ready to touch down in the Indian Ocean after it has successfully gone through the atmosphere and gone through the reentry, and it's survived to this point. And I would use the word survive loosely.
Oh my gosh, I remember that. That was incredible.
Yeah. So, what you see here is there's a lot of missing tiles. Part of them were on purpose, and people go, why would you take the tiles off on purpose? And it's for a very good reason, is that they're trying to figure out what the robustness of the ship design is, where are the critical parts and what are the non-critical parts of the ship, and how much of the heat shields could they lose, or the tiles, and in what patterns and in what parts of the ship so that is it going to be a mission failure or is it going to be, yeah, we're going to have to do a lot of renovation when it gets back, but it's going to get back. So they're really trying to test all that out. They were also testing in a variety of different flights, different kinds of tiles, whether they're strengthened, where they have different ways of attaching to the ship, whether they're different sizes, whether they're different materials. The last flight, the Flight 10, they tried some metallic tiles. And in this case, they tried groupings of 4 tiles in various different spots gone. So it was all of these tests were all the way through the Starship program up to now. And it's one of the reasons why when flight, what was it, 7, 8, and 9, or 7 and 8 kind of blew up and didn't do well. It was really bad because we didn't get all this data. So it was really important for the heat shield guys to have it go through the atmosphere so that they could see the results of the reentry.
You're talking about the booster now, or the
No, I'm talking about the ship.
the
Because
ship?
remember
Okay,
when
yeah,
a flight, I think it was 7, it blew up over the Kirks and Caicos over the Caribbean, and
yeah, yeah.
then flight 8 did the same thing, and then flight 9 came back uncontrolled
Hmm.
because it had basically it had a leak, a
Yeah.
methane leak in the nose cone. So they weren't really able to get any data. So they've got the data from flight 10 and 11, and this is an example of that. A couple other things that they see is you see the orange color. It's not as bad as flight 10, but it's basically the oxidation, and it's caused by that atomic oxygen in the plasma field interacting with steel and causing it to rust or oxidize very rapidly. And in this case, it was the stainless steel itself.
Yeah. So
All right, how
we
many ton of fuel versus booster empty weight? Well, the booster has something about 3,500 tons, 3,500 metric tons of propellant in it when it lifts off. And when it comes back and it's caught, it probably has maybe 100 or maybe 150, something like that. So the vast majority of it is gone.
it's good to understand those numbers, right? Because the difference is so massive when it's full versus when it's not, right?
Right. Well, remember I was telling you that the center of gravity on rockets changes faster than anything else, more than a race
Hmm.
car, more than an airplane. And that creates a lot of aerodynamic issues that they have to overcome.
Yeah.
Um, but on this picture, I did a couple of things. Is there were burn throughs, which was important to find out where that was going to be. And then there was depressurizations. So let's go to the next slide.
Yep.
And this one's going to look a bit strange, but there's a kind of a history lesson here. And it's important if you're going to be an engineer and you're going to be doing the analysis of a rocket, of the Starship, of an airplane in this case, to figure out what is this story? What is it actually trying to tell you? And how does that inform you about the actual strength and the ability for that ship or that Starship or the airplane to be able to do its mission? This comes from World War II, and there was some analysis, battle damage analysis of aircraft that were coming back, and you can see where all the damage was. And the initial reaction by a lot of engineers was, oh, we need to reinforce these parts of the airplane because this is where all the battle damage happens, and we need to make sure that it is able to do its mission and it's survivable and it protects the crew. But that is totally the wrong message, the wrong lesson to learn. And it took some maybe more engineers that have a little bit more perspective to point out that no, this is actually okay because these are all the non-critical areas of the airplane. Or in the
Hmm.
Starship, these are all the non-critical areas. If it burns through part of a flap, but it still is able to come land, it's not great, but it's still able to do its mission. So it's
Hmm.
all the other areas that are important because none of those airplanes ever came back. So
Hmm.
this analysis, by doing what they did with Starship and removing tiles and doing all the various different tests they did, really helped nail down for the design that they have, what are the critical areas, what are the non-critical areas, and how their airframe really does perform in a variety of different scenarios. And this is really important as they build on their lessons and we get closer to the point where we start putting humans and payloads onto
Hmm.
the Starship. So, that's the point of this. And the dots, the battle damage, kind of look like where tiles were removed from the Starship.
Yeah, that makes
So,
total sense. It's basically having them ready for the future eventualities that they still don't know. They're trying to simulate those by
right,
making it vulnerable and being able to find out how it's going to react.
right. And you won't know until you actually fly it. So they
Hmm.
deliberately did this, and they've got so much more data than I think most people know. And they have a really good idea of how that design actually functions. So we can go to the
Yep.
next slide. And going back to the what's critical and non-critical, what you see here is this is ship 38 as it has finished going through most of the plasma. It's still in the atmosphere. It's still on that final approach. And you can see that one of the tanks, I think in this particular case, it's the oxygen tank, has depressurized. And you can see, they used pressurization within the Starship to provide rigidity of the structure. When they had the burn through, they lost that pressurization. So, and there's no engines, there's nothing running to try to, fill it back up. They use autogenous generation of the gases from the engines to pressurize the tanks. Well, that can't happen right now because the engines aren't running. So, if they need pressurization to provide the rigidity of the structure of the Starship, and we're seeing that it's depressurized, what did that tell them? Well, it told them, one, that this, for the purposes of surviving and being able to land, that this is non-critical, which is great to know because the ship was still able to perform despite having a tank that was depressurized. Now, some people may ask, well, how did it light the engines if the tanks were depressurized? And that's because they don't use the main tanks for the landing burn. They have header tanks, which are completely separate, and they're up at the top of the nose. And part of the reason why they're at the top of the nose is going back to that center of gravity, center of pressure of the Starship. You need to have the weight distribution proper within the Starship to be able to keep that controllability. So they have the header tanks at the very tip of the nose to make sure that the center of gravity is where they need it within the Starship to be able to be controllable through the atmosphere. So completely different systems. Those would be critical because without those, you can't land. But with a depressurized oxygen tank, because of a burn through, the ship still survives. So that's huge, huge data that they got from the last flight. If you go to the next visual, what you can see here is kind of that same area. It's still deformed, maybe not quite as much, and it's kind of just off frame here. But people might remember when they saw the video of this coming back that there was kind of a stream of white gas, whatever, coming out of the burn through of the oxygen tank. The reason why there was a stream coming out of that burn through and some of the dents were popped back out is because the engines are now running, and it was using the autogenous pressurization from the engines to feed gas back into the tank, which was giving it a little bit more pressure, and it was forcing out the gas through the hole. Does that make sense? No? Uh-oh. I think you're frozen. I can hear you now. So did that make sense?
Okay. Yeah, yeah. I was saying, I don't know if you can hear me again, but I noticed there's a nasty damage, right? There at the bottom part.
Yeah, well, that's an area of the kind of the interface between the flap and the body on the aft flap, and that's where they had actually removed, I think, a group of 4 tiles. So as it was doing the reentry, the tiles allowed it, because they didn't have any backing. They had no ablative material or anything. They just had the steel, and they wanted to see what would happen. So the tiles burned through. It started affecting that, and also because the tiles were not there and they were getting damaged, as it got farther into the atmosphere and you had higher that density and you had more of the aerodynamic forces, it just started peeling things off from that interface.
Cool. So let's move on to this other one where, yeah, let's explain what's going on here. This is a prediction, right?
Yeah, so we talked about the heat shield. That's an important thing that they need to nail down, and they've got a lot of data, but they're going to still need to do more tests on that. The other critical capability that they need to basically build and demonstrate this year coming up is on-orbit refilling. And that is going to be very important because, one, without doing any on-orbit refilling, it's kind of like having a Tesla car that has no superchargers. You can still charge them at home, but when you get a little bit of distance and you need to charge and there's no superchargers anywhere, it makes you very limited in what you can do. But with the supercharger network, now you can take the cars and go all over the place. It's the same thing with on-orbit refilling for rockets and Starship. Is because of the strength of gravity of the Earth and the way something called the rocket equation works, is that the bulk of your fuel is used up just getting into low Earth orbit. So when the Starship gets to low Earth orbit, it's almost completely empty. So for it to go onto the moon, to Mars, to do any other missions, it needs to be refilled. And to do that, they have to build basically two types of starships. You have to have the receiver starship, the one that can take the fuel, and you have to build the refueling starship, or the tanker starship, that can give the fuel. So they're going to need to have two different designs that they are able to come together. And this is the latest illustration of how Starship's going to try to work. They'll have 4 mounting points to kind of bring together and hold them together. And then you have to be able to do the transfer of oxygen and methane, and do it in a microgravity environment. And at the scale that we're talking about here with starships, and we're talking about to fully fuel a starship, you're going to have about 1,200 to 1,500 tons of cryogenics. And that's going to take multiple tanker ships, a lot of time, and a lot of other complications. But it's never been done. But it's critical. It has to be done. And so this must happen this year.
Yeah, that's insane. And which brings to, so Luis is asking which version of the Starship will support ship-to-ship refueling, or filling.
Yeah.
You'll be guessing, right? Like there's no way of knowing.
Actually, we already know. Version 3,
the
Ship 39, which is the first V3 of the ship, already has they're basically like 4 mounts. There's 2 of them that are right underneath the payload, the Pez dispenser, and then there's 2 that are farther down aft on the ship, on the leeward side, the non-heat shield side. And they're already stacking that ship right now. So 39 is going to basically be the first flight of V3, and it's most likely going to be suborbital and land back in the Indian Ocean, just so that they can test the design. But they've already designed it into the ship. And like I said, there's going to have to be 2 variants. You have to have the receiver, which 39 would be, because it has the mounts to allow the tanker to dock with it and to have that transfer. So all of the V3s already are built to support on-orbit refilling. We just need to get them up there and then start demonstrating it. And SpaceX needs to learn, how does it actually work? How does the hardware work? And how does the design work to be able to do that on-orbit refilling?
So it's basically going to be version 3, A, B, C variations of it, so they know, or is it going to be basically the same one where you can almost like use them for one thing or the other?
No, I think for a while, if you look at this design here, you can see the difference between the tanker and the receiver. The receiver, I was a tanker pilot, so that's where it comes from. But the tanker and the I guess the receiver has kind of those projections that are built into the hull, like I said, and they're the ones on the bottom. And then the tanker has kind of those probes that will extend out, and then they use those 4 points to make sure that it's oriented properly, and it allows them to come together to be able to dock, so that they can then do the propellant transfer. So you're going to have 2 different versions of that. And for right now, for 26, we're mostly focused on them demonstrating the capability. They really have to. But somewhere down the road, if you start thinking about the operational cadence of launches of starships, when there are hundreds of starships going up, is probably the one version of the Starship that's going to be launched the most will be the tanker, because you're going to need multiple tankers for every Starship that's going to go do a mission. So there's going to be a lot more tanker versions than the receiver versions, at least early on, and the cadence for that is going to have to be extremely high. One of the ways to address that is to have on-orbit depots where the tankers go up and refill the depot. You have like a giant fuel tank waiting for the starships to show up, rather than a starship having to wait for all the tankers. And I think that's going to come, but it will be a little bit later down the road. They first need to demonstrate this capability. Without this capability, Starship cannot do any of the missions that we've heard about, Moon, Mars, or anything else.
Yeah,
it could probably it might be able to do Starlinks, but that's about it.
Yeah, well, that makes sense. I think this is a good question. I think I know the answer to it, but can you dig in a little bit on that question and answer it?
So is the refueling there to avoid a 3rd stage going to Mars? Well, the whole system is designed to have a fully reusable Starship. So they've designed it so that refueling is part of the deal. So that was the way it was designed. Trying to have a third stage, even if you did, then you start running into the rocket equation. I call it the tyranny of the rocket equation, because as you add more structure, you add more mass, you add more propellant, then you need a bigger rocket. So you need a
Hmm.
bigger rocket, so you need more propellant. And so eventually it gets to this point where it's just
Yeah.
not worth it.
Hmm.
So instead, the way to kind of cheat the rocket equation is on orbit refilling. So it doesn't matter if it's Starship or anybody else. Blue Origin is going to have to use on orbit
Hmm.
refilling as well.
Yeah.
It's right now, as long as we have a chemical based combusting and we basically use up all the propellant as the process of making the thrust. As long as we are forced to have this technology, we need to have on orbit refilling. There's just no way around it.
Yeah, it makes me think about all the people that are always screaming, "Oh, let's use nuclear," right?
Well, nuclear would be okay, but most likely for intra space, like going from the Earth to the Moon or Earth to the Mars and having it kind of a cycler type thing.
Hmm.
Um, but trying to have it so that it has high thrust uh, to get out of the gravity well is probably maybe not what nuclear is best suited for. And
Hmm.
besides that, I think you'd have a lot of people pushing back on using nuclear rockets in the atmosphere. So there's a
Hmm.
variety of reasons for that. But ultimately, we have a consumable based chemical rocket technology that is kind of, you know, forced to have to deal with the tyranny of the rocket equation. So anyway, so I think when they were looking at the design, they look at all of these factors, and this is the design that they've centered on,
Hmm.
and that's the way it's going to be.
Yeah, that makes sense. So let's see if we can. We have. I mean, I know we can extend a little bit if we need to, but since we have about half an hour left in the timeline
Okay.
that can we talk a little bit about the timeline? Like, when do we expect the next test flight, and when can we expect the first orbital flight? And I know we have like this map here
Right.
that shows what Starbase is going to look like. Can you go over some of those details and answer those questions?
Yeah, so that's a very good question. I kind of hinted at this before, is that the next flight, Flight 12, is going to feature a brand new booster, new design, a brand new ship, essentially a new design. And of course, this, which is the orbital launch system, which has a brand new tower, a brand new flame diverter, brand new orbital launch mount, and brand new cryogenic farm and water deluge system. Everything is brand new. So and it's still, all three of those big components are still in the process of being built. So when will the next flight be? Well, a lot of it has to do with when is the orbital launch site ready to go? When is the booster ready to go? Which means that they've gone through some of their testing. And when is the ship ready to go? Which means that they've gone through all that testing and they're ready to do a full stack. So because of all of these facts, I don't think it's going to be anything earlier than February would be like amazing, probably more like in March. And if anything goes wrong along the way, maybe it would push it a little bit later. Um, Now, some people are going to say, well, that's way too long. Why are they waiting so long? Well, they're not really waiting so long. I will remind everybody that Ship 36 was being tested at Massey and it blew up.
Mm-hmm.
Was another V2 ship, which should have launched on Flight 11, which means we would still have had one more launch of the V2s yet to go. So they were planning on that. So we would have had another one more final launch of the V2 ship and booster. In fact, Booster 17 is stranded now because it doesn't have a ship for it, and it's going to be scrapped because 36 blew up. So they had already planned for that. That would have cut the gap a lot. And also, it's just they're building completely new systems, and I think that they want to make sure. I mean, these have to actually perform well because this is going to be essentially hardware that's going to be used for things like the Artemis program. The on-orbit refilling is going to be critical for any mission, and just the design of the ship. the ability to be rapidly reused. We haven't even seen a ship caught yet. So there's a lot of big milestones that yet have to happen. So I think that they really want to make sure that everything is good to go before they do the next launch. So my guess is earliest February, probably March, maybe a little bit later for the next flight. And then if that goes well, meaning that there's no FAA investigations, there's no loss of the tank farm or anything because of accidents, whatever, then I think we're going to start seeing them pick up the pace a little bit more. But it also depends on the amount of hardware that they build. There's a lot of ships that are in various stages of production within the Star Factory right now. I think it goes all the way up to like maybe ship 44 or so. So there's a lot of them. I haven't seen a lot of boosters, and that's going to be important. And even if they do a lot of reuse of the boosters, which is going to be critical, they're still going to need some. And they've only got one that's not even finished yet. So, so what do I think? 12, like I said, February to March, April, something like that. And then after that, a rapidly increasing pace. They'll probably, maybe get through, if we're lucky, flight 20 next year, which would be great. Maybe a little bit more depending. And then of course they also have Kennedy Space Center coming online later next year. So there'll be more options that are coming up. The other thing to keep in mind is that the tower that we've been using all the way up to this point, that orbital launch mount and everything, it's all being demolished right now. So it's no longer available. So there are no towers. There's no launch mount right now for Starship anywhere in the world that can be used.
Before we jump into the next one, which is like probably the most exciting thing for me, I wanted to ask you, that ship that exploded in Massey's, was it because of the header tanks? What was the reason for it?
It was basically, well, I'll tell you the technical reason, and then I know that some of your viewers might know that there's a little bit of a backstory there too. The technical reason is that one of the composite overwrap pressure vessels, which had, I believe, nitrogen in it, and it was arrayed inside the nose cone. In fact, when we saw that the payload door open and we saw the satellites going out, if you pay attention, you can actually see them kind of along the wall, the inner wall of the nose cone of the ships. Well, one of them failed at a lower pressure than what it was supposedly rated for. And I think it's something like 1,000 PSI. So when it went, it pretty much destroyed a lot of the ship, and it had methane and it had oxygen in the tanks, at least a certain amount of that. And so that just cascaded and it just basically destroyed the whole thing. The backstory is, I don't know, have you heard the backstory?
Not really, because I've heard different versions, and I think you explained something to me, which is what I wanted you to discuss, because I wanted people to understand that. But it's fascinating, especially when rumors start like circling.
Yeah. Well, I think maybe the PG version of that is that COPVs are very prone to damage if you don't handle them properly. And there's some thought that maybe the handling of the COPVs wasn't as good as it needed to be within the operations of SpaceX, and possibly one of the damaged COPVs made it onto the ship. And then when it was pressurized over and over again, it eventually got to a point where it failed. So they've instituted a bunch of new processes to make sure that the COPVs are well insulated. You'll actually see that on some of the in the production line. If you go down to Starbase, you can actually look through the glass and you can see, certain stages of them being put together. But they have like a mat or a blanket or something around them as they're handling them before they're installed into the ship. Interestingly enough, there was a Falcon 9 that was lost with a payload. It actually had to do with Mark Zuckerberg's payload, but it was lost for the same reason, or a very similar reason, and it was that COPV. So it's not out of the question that it has happened and it could happen again, but I think there was a lot of lessons learned with that.
Yep. Right on. Okay, so I'm excited for this one because I've been waiting for this. This is like the super exciting part for me. Let's talk about the orbital flight ship return to the launch site
Yeah, real quick,
based.
one person had a question. Are the starships designed to return to Earth from Mars? And the answer is yes. So the
Oh
idea
yes.
would be
Hmm.
is that they would go to Mars, they would land, they would do in situ resource utilization of various various means. Sabatier process, which is basically uh, extracting oxygen out of the carbon dioxide, and then with water they can get hydrogen, and through that process they're able to make methane, and with the oxygen and the methane, then they would be able to refill the ship and then come back. Um, all that being said, that's very hand wavy because there's a lot of technical details, a lot of logistics, and the ability of building those systems on Mars is completely untested. So, um, my guess, this is just my guess, so take it for what it's worth, is the first several flights of starships with people to Mars are going to be one way because the people are going to have to be there to build the infrastructure that over time would allow returns back to the Earth. But that's just my guess.
Hmm. Kind of scary.
Well, I mean, but it's like going to the New World back
Yeah.
in the,
Yeah.
the ancient days.
Exactly.
Is you
Yep.
left your home, you left everything, you got on a rickety boat that you hoped would make it, and you knew
Yeah.
you weren't coming back.
Yeah, 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 absolutely. You know what? Arne Carlson, which is the person that asked this question, also asked earlier, why is it called the PEZ? Uh, when they were showing the Starlink satellite dummy being like tested, and
Yeah.
that one, I'm proud to say that I know the answer to
All
that
right.
because
What's the answer?
I'm the kid from the 70s and 80s, and the PEZ dispenser was this little candy thing that had like a head that you would pull up and it would spit out the candy.
Right.
And the PEZ dispenser is what they're emulating with this, right?
Right. Exactly. So, so that's where it is. A little bit of ancient history there, but you know, this is just one of the various different deployment mechanisms and ways that they are the Starship designed. Eventually, they're going to have much larger doors of some sort, and also with the HLS lander, they're going to have a way of having a kind of an elevator kind of thing with a boom that extends, and then you have a cable to go down. So
Yeah.
they're going to have a lot of different variations of the Starship, and the payload door will be what that is. But right now we're stuck with the Pez dispenser.
Yeah, yeah. And you know what? I can't wait to see this thing at least on the moon, man.
Yeah,
Something from SpaceX on the moon would be fantastic.
hopefully in a
So,
few years.
yep. Joe, let's talk about this Starship orbital return flight path.
Okay, well, this is really exciting because it's something that nobody has ever seen before because it hasn't happened yet. But on Flight 11, SpaceX actually went through the maneuvers and they actually flew Ship 38 through this entire trajectory over to the Indian Ocean to prove that it would work. And so we not only have the theoretical data and the computational fluid dynamics and the all the stuff that SpaceX go through to design the ship and design these trajectories, but we actually have now flight data that says that we can do this. And so what this is the space engineer who does a lot of great work, took a look at the video, the telemetry, the data that came out of Flight 11 and came up with this flight path, and he overlaid it onto South Texas so that we would get an idea of what it's going to look like when a Starship returns from orbit, which it hasn't achieved yet on purpose. But a couple of things that I would just to set this up real quick. Well, first of all, this shows you the red line is the ground track of how the Starship will proceed from the west to the east, heading over northern Mexico across the southern tip of Texas, and then down along South Padre Island to the catching point. The gray line shows the altitude and the vertical path that it would be on. Um, let's see. Go to the next slide real quick. What I'm showing on this is where the Starship will be coming from. And as I said, this is something nobody has seen yet because the Starship hasn't gone to orbit. And one of the important things that I want to point out is right now, up until now, every single flight, it's launched, it's gone up for the hot staging, the booster has come back, it's either been caught or it went into the Gulf, and then the Starship just went on a suborbital and landed the Indian Ocean. So we're kind of accustomed to the booster going to the east and coming back from the east and landing back where it came from. The Starship's going to be totally different. And also the booster does that within about 7 minutes. It launches and about 7 minutes later, it's back at the tower. It's very quick. The Starship, on the other hand, is going to go to orbit. And when you go to orbit, that means that it's going to go around the Earth. And every time it goes around the Earth once, the Earth rotates a little bit. So that means that the phasing of where your orbit is to a ground track is different. So you're going to have to go through multiple orbits until that ground track lines back up again. And for each orbit, it's going to be approximately 90 minutes. So they're going to have to go probably, I don't know, maybe 10 orbits or so. So we're talking, it'll be another day at least before the ship comes back. So it's not going to be, you go out to see the launch and we're going to get a double catch with the ship and the booster right away. It's going to be hours or days later. And the ship is going to be coming from the west to the east because of the orbital trajectory that it's going to be on. And this is what it's showing here. This came from an environmental, assessment that SpaceX did with the FAA. So this has been approved. And this shows you the flight path coming over the Pacific Ocean, over northern Mexico, crossing Baja California, going across the tip of Texas. And then you note at the very end, it does this little bump in the trajectory. And that's what they tested on the last flight. So go to the next slide real quick.
Yep.
This is, okay, so this is zooming in a little bit more. We're seeing the Starship. It's over northern Mexico, and it's going to come in. You see that kind of bump in the trajectory. The reason why they're doing this is that this trajectory is optimized to avoid as many or all population centers along that entire route as they can. And the bump allows it to go north of Harlingen, north of Brownsville, north of, I think, Richardsville, and then orient itself on a north to south trajectory to get to the tower. And if you go to the next slide, this just zooms in a little bit more, and you can see that's going to look. So, we'll show you in the animation, but if you were at Isla Blanca Park at the very tip of South Padre Island, it's going to fly directly overhead. It's going to be pretty amazing. So let's go into some of the, and this is what I posted the day after the launch. I was kind of working with the space engineer a little bit, and he had this path. I actually kind of did a little bit of an animation on it, but this kind of shows that as well. But anyway, this is all based on the space engineer's work, and I want to highlight that. And again, you can go to his channel, also on X. There's his handle there, and you can follow him as well. So I think we're ready for the animation now.
Yeah, absolutely. Let's jump right into it.
Okay. So like I said, this is based on actual trajectory and flight data from Flight 11. And just to orient yourself, on the upper right is the video from Flight 11. So it's showing what the ship is doing at the same time that we're seeing the animation. On the left is following the ship in as if you're flying right above it. And you can see the Gulf and the blue off the horizon coming in. The bottom left will show you that ground track. Right now, we're just outside of that map. And then the other ones kind of show you specific parts of the ship itself. I guess the one next to that map on the left-hand side, you can see the pitch of the ship. And right now, it's pitched up about 70 degrees. It's trying to maximize that area, that surface area, to the atmosphere so that the atmosphere can slow it down. And that creates all the heating, and that's why you need the heat shields. But you can see here we're at about 48 kilometers, and that's pretty high up. That's about 35 miles above the surface of the Earth. That's 7 or 8 times higher than what you would see with a typical commercial airliner. You can also see that we're at 11,000 kilometers per hour. That's pretty close to we're firmly in hypersonic speed range. So we're really moving very, very fast. And you can see that the altitude is slowly coming down. The speed is coming down. You can see the G forces. And you can also see as we are approaching the coast, and you can start seeing a little bit of South Padre Island there. So we can fast forward a little bit, maybe to like 2:45 or so, if you can move there.
There you go.
Okay, so now we've gotten much closer to South Padre Island. In fact, you can see that right on the center, and then to the left of the screen, you see the Gulf, and you see the altitude. We're still at about 40 kilometers, which is still pretty up there. It's about 20-ish miles or so, and we're at 6,000 kilometers per hour, so it's still moving very, very fast. Now, I mentioned that they wanted to do this to avoid most of the population centers. Which is true. But another thing that they're doing with this trajectory and this turn that we're going to see is that if something goes wrong with the ship at any point here, it has enough altitude and it has enough speed that it will continue off into the Gulf. And it would basically divert into the Gulf and not pose a hazard to the population. So the whole purpose of this is to do that. You can also see with the ship on the upper left that it's banking now, and this is part of that dynamic banking maneuver. So the ship is still pitched upward a little bit, not as much as 70 degrees. In fact, it's starting to pitch down a little, but it's at a pretty high bank. And so the trajectory is taking it over the Gulf, which is that divert option. It's also creating a lot of lift. And with that lift, if you remember back, we were talking about center of gravity, center of pressure, and also the types of drag. This is creating a lot of induced drag and body drag, and it's slowing the ship down considerably. You can see we're still at 30 kilometers, which is still about 15 miles up, or about 3 times higher than the suborbital Starship flights that we saw early on. So it's, even though it's directly above South Padre Island right now, it's still quite high up, but you would still be able to see that. And you can see how the speed is continuing to just bleed off. You can also see that it's starting to turn more and more towards the west. And I think what this is doing is it's using its aerodynamics to arrest the trajectory into the Gulf, and it's now redirecting it towards the towers, the tower for its catch. So that's why it's pointed in a weird location. We can also see that it just went subsonic, but we're still at 20 kilometers up. So it's going to take about a minute, maybe 45 seconds for that sonic boom to reach us at Isla Blanca Park. So right now, we would definitely see the ship. It would be very quiet because we haven't heard it yet. But you can see, what the ship is doing with its trajectory. It's flying its way now. It's arrested that trajectory into the Gulf, and it's now kind of stabilized, and it's getting ready to maneuver into that, basically the body, the coming straight down that belly flop. And you can see the speed is impressively slow, only 600 or so kilometers per hour. It's at 12, coming down to 11 kilometers. In 1 more kilometer, it will be at the same height that we saw the suborbital ship demonstrations that they did with SN8 all the way through SN15. And now it's pretty much completely in the belly flop, and it's falling almost straight down. And you can see the production facility of Starbase off to the right in the upper left, and directly under the nose of the ship is the tower. And you'll note that it's still facing to the west. And you're like, wait a minute, why is it facing west? We're really close to the tower. And that's because it's about to do its reorientation turn. So you can just imagine what this is going to look like for real. And very soon, we're at 6 kilometers, you're going to see the ship start pointing to the south. And the other thing to point out is, look at the speed, 420 kilometers per hour. That's about 250 miles per hour. So it's quite slow. It hasn't used any of the engines yet. And also look at the fact that the engines haven't lit yet, and it's at 4 kilometers. You can see the tower already. And it's going to look just bizarre. Everybody's going to think that it's way too late, that it's not going to survive. But just watch how far it just continues on. It's pretty
Just get
much
so close.
I know it's pretty much oriented the way it needs to for the tower. And if you remember, the tower too is facing to the south. It's different than the original tower. So this is all designed for the tower design and its orientation. And look at this, we're at 1 kilometer, and now the engines come on. Look at the tower. It's like we're virtually right on top of it. It will go over the tower. It'll arrest its trajectory to the south, correct, come back down, and it's going to caught. And so that's what it's going to look like for the actual return when we have an orbital Starship.
That's insane. That's bizarre. It's so crazy.
It is. It is. So let's go to 1555 on the time.
So this
What
is
this
the
is this is a great illustration of if you were standing at Isla Blanca Park,
hmm
looking up, what it would seem like. You can see kind of the rays going up. That's the sky, the round part of the sky. You can see that path, and you see the little dot. That's the Starship coming in. And from Isla Blanca Park, looking to the north across all of the hotels and where the big blimp, the aerostat would be, and the causeway off to the left, you would see the Starship like a dot coming in. At this point, it's still 37 kilometers up. So, that's about 25 miles up or so. But it's coming in really, really quick. And if you want to accelerate it a little bit, maybe to like 19 minutes or so.
Okay. Remind me again, at what point is that it's last second that it lights up again? It's when it's about
A
four
little less
kilometers?
than 1 kilometer.
1 kilometer. Oh my God.
Yeah. Which is 600 feet something. It's ridiculous. So
Yeah.
here is you're standing at Isla Blanca Park. The Starship's already gone subsonic, but the sonic booms haven't quite hit you yet. But if you were looking up, it'd be almost directly above you at 6 kilometers.
hmm
And and now as you look to the south, I guess what this is the trajectory coming down towards the tower. The red dot is the Starship. This is what you would see looking across the channel from Isla Blanca Park. You can see the two towers. You can see the production site off to the right. And you can see, just imagine what this is going to be like when you see the Starship coming into the tower and how close to the tower it gets before those engines come on. I think this is just going to be I think this is going to be the biggest, the highest demand launch and recovery ever in the Starship program when they do it for the
Yeah.
first time. But look at this. They still have another 600 meters to go before it gets to the engines coming on. Maybe a little bit more than that.
So
Look at
right
that.
about
Right there.
there. Yeah.
Just look how close it is.
hmm
It's crazy. And if you've been to Isla Blanca Park, your actual visual, as long as the atmosphere is not too misty, whatever, is better than this. You'd see it
Yeah.
crystal
hmm
clear.
Yeah. It
And
reminds me
one
of the.
one more, yeah, let's go to 2430.
Okay. That jumped
Yeah,
a
what?
little bit too far. Let's bring it back a notch.
Yeah,
So
2430 or so if you can.
here.
This is actually from the tower view.
Yeah, so it's at 24:20 right now. 10 more seconds to get there. It doesn't let me add fractions of
Oh,
seconds.
okay.
So
Well, this would be if you were on Tower 1 watching the launch, so you'd be that
mhm,
close.
yeah,
And so I don't know what the next one will show. Ship Dune. So this is actually good. If you've ever been out to Starbase and you've standed on the dunes and the mud flats out right next to the orbital launch site, if you were standing there, this is what it would look like with the ship coming right at you.
mm,
It's pretty amazing. And just again, look how close to the tower it is and how short a period of time it has to arrest the descent rate, correct its trajectory, bring it over for the chopsticks, and then have the chopsticks catch it.
mhm.
And this last one is if you were at the Mega Bay at the production site watching the landing, what it would look like. So
Unbelievable.
so anyway, so I mean that covers most of everything, and I don't know if people have questions, but I want to say thank you to the space engineer for putting these animations together. This is from the Star Factory. Um, but it really gives us a great idea of what to expect for the first catch for the ship and maybe where you want to be to watch it.
Yeah, which reminds me, I'm gonna pull the next slide here because I have the
Oh yeah,
I actually captured this. You were standing next to me from
yeah,
4 miles away from the launch pad. I'm sorry, the capture tower,
right.
uh, and I muted the audio of this thing for this particular clip. But this is kind of the distance that you can be from the opposite side of the
Yeah,
launch.
yeah. If you were at Isla Blanca Park, it would look kind of like that, but
Yeah.
with a ship coming into the other tower. The unfortunate thing is that the tower will kind of block the view of the ship at the last second, unlike here where the booster's kind of landing to the side of the tower.
Hmm.
So plugging for Rocket Ranch and being over at the Raptor Roost area where they can watch the landing, that would be the best place because then you'd see the ship kind of on the side of the tower coming in.
Hmm.
But yeah, so
Yeah.
this I'm glad that you put this up because it really helps people get an idea of what it really would look like from just about 5 miles away.
Yeah, I mean, I captured this one with my Canon and not a very large lens. It was just I think it was like a 70 millimeter lens that I used for
Okay.
this one. So it gives you perspective of how close we can get, even when the rockets are either launching or coming back to the base. Let's call it the base.
Yeah.
So yeah, I mean, this was incredible, Joe. I know a lot of people have very few chances to hear you talking in detail like this about rockets, but you and I talk about this stuff all the time behind closed doors, and it's fascinating to learn all these things. I'm super excited about what SpaceX is doing right now, and I
Yeah.
can't wait to see where they take everything to the next level.
Yeah, me too. It's just, I didn't make you aeronautical engineers, but I'm hoping with just a little bit of talking about some of the considerations and the aerodynamics and all of the challenges that they have, I hope it gives you a great appreciation for the people that are actually building that hardware. It's truly inspiring to me.
Totally, absolutely, 100%. The future is super, super exciting, and thank you again, Joe, for everything that you provided us here. Thanks to um, your friend that provided with all the animations, the rocket engineer
The space
and
engineer, yeah.
space engineer, and
Yeah.
I also want to thank absolutely every one of my subscribers and followers that have been joining us during all these different things. We talk a lot about electric cars, we talk about rockets, we talk about having fun with your friends and the future of human space flight, and I cannot be providing all this content without the support of all the subscribers and followers that are in both our channels. So thank you everyone for joining us. I think there are questions on X that
Okay.
I'm trying to find right now. Let me see if right now I am looking at just what we have here on screen and I don't see any new questions. So maybe I can poke my head a little bit over um, the X. Let me see real
Okay.
quick to see if I can see it over there. Um, I'm
By
actually
the
going.
way, if you are really interested in a lot deeper discussion about aerodynamics, I do have uh, aerodynamics of starships video on my YouTube channel. And you're welcome to go to my YouTube channel and take a look at that. It goes into it much more in depth. It's ultimate geeky, but hopefully with what we talked about today, and when you see that, it'll make a lot more sense.
Yeah, totally. And unfortunately, I can't really find. Nancy said that there were some comments on X. I just can't find them. So, however, feel free to, whether it's on X or on YouTube, under the live stream, feel free to post any questions. We're going to take a look at them and maybe we get a chance to respond right there on text. If not, don't forget to follow Joe on YouTube. He's doing incredible flights over Giga Texas as well, and every now and then provides some space related content. Also on X, his handle is the same, Joe Tegtmeyer. And thank you all for joining me. My name is Rafael Teslatino on the Spaces. So I hope you come back for the next one. Joe, any final words?
Just thank you very much for having me on. As you can tell, I enjoy talking about space and everything. But most importantly, is I just hope that I'm, helping you understand what is going on and get a lot more excited about what we're seeing, and maybe just understand a little bit more behind the scenes of why did they move those fins? What are they doing with the heat shield? Why are they doing all of this testing? And it's because it's hard work, but it's necessary for them to have a system that does things that we've never seen before. A lot of people talk about going to the moon, and we've already been there with Apollo. What's the big deal? It's kind of like the difference between taking a Cessna 172 and flying it around and think, "Oh, I'm flying," and getting on a 747. Totally different.
Totally
Totally
different.
different.
Absolutely. Thank you, Joe, for that. And we'll see you in the next one, everybody.
Okay, take care.
Take care.